Good day, everyone, and welcome to our Vaisala Leosphere Leading with Lidars webinar series. My name is Greg Shambo, and I'm the Leosphere Weather Business Manager for North America, based in Boston, Massachusetts. I'm joined today by two industry experts. Philip Herbert is an experienced data analyst with a deep MET background with Pattern out of Houston, Texas, and Philippe Pondrian is an expert in remote sensing at Renewable Energy Systems, RES, located in Broomfield, Colorado. I'm extremely happy that these two people with so much industry experience are willing to share their story with us today. We have a very full agenda, so I wanted to point out the top 3 things that you're going to learn from our speakers today. Number 1, there are some issues to be aware of and gotchas that you want to avoid when standardizing on remote sensing. Number 2, we're going to go through a concrete example of how you can calculate return on investment for these remote sensing devices. And finally, number 3, we'll take a look into the future to see where the technology is going and how a new approach might enhance your business. For those of you who are not familiar with Vaisala, real quickly here, we're the leading vendor of Vaisala weather instrumentation and equipment around the world. We've got over 1,900 employees, 30 plus offices, and we're no strangers to remote sensing. We've developed a variety of sensors such as our Vaisala lightning detection network that you can see in the lower left-hand side of the slide, our present weather detectors that use infrared light to detect different types of precipitation, and our oscillometers using lasers that can detect cloud heights and cloud cover. And of course, our Triton Sonic Wind Profiler that is arguably the first commercially viable remote sensing system designed for the wind industry. We've been doing this kind of thing for many years, and with the acquisition of Leosphere in 2018, we've added 4 key remote sensing devices to our portfolio that we now offer into a variety of different markets. I'm sure most of you are familiar with the WindCube in the wind energy space. It's also used in air quality studies, as is the WindCube scanning lidar. The nacelle-mounted units are called WindIris and are useful for a variety of applications, including power performance testing. The turbine-controlled nacelle-mounted units we sell directly to the turbine manufacturers who are integrating them into their hardware offering today. Now, one of the hardest things for us as a vendor is to keep up with your demand. I'm happy to say that this year, we dramatically expanded our manufacturing capabilities, and we opened a new Leosphere headquarters and factory near Paris, France. There you can see on the bottom of this slide the test facility, which is located on the top of the building. We also just opened a brand new factory over in Shanghai, China, to help us meet the demand in that market. Combined, we now have the ability to produce more than 1,000 lidars per year, and we're ready to scale that up when the demand needs it. Before we get started, just a few housekeeping items. Everyone will be on mute. Your video cameras are disabled. If you have any questions, please send them through the chat window on your screen, and I'll try to address all of the questions at the end in the Q&A session. The ones I can't get to, I'll personally follow up directly with a response. Lastly, I encourage everyone to stay until the end. There's going to be a late-breaking announcement from the Consortium for Advancement of Remote Sensing, or CFARS group, that is sure to benefit all of us. Okay, let's jump right in. Pattern is an independent renewable power developer. Its sister company, Pattern Energy Group, owns 28 projects that total over 3 gigawatts of capacity. Pattern Development continues to grow their development reach internationally. Philip, one of our key speakers here today, has a BS in meteorology from Oklahoma, and he currently manages all of Pattern's MET campaigns in North America. Philip, if you're ready, you can take it from here.
All right. Thank you, Greg. Appreciate it. Good afternoon to everybody in the center and eastern part of the country, and good morning to those of you that are on the out west and on the West Coast in the mountain time. Wanted to take you all through kind of our realization about 9 years ago or so that temporary Met towers by themselves were really no longer going to cut it for standard wind resource assessment. At that time, Pattern Development's pipeline had projects that were mostly using 50 and 60 meter Met towers and really nothing else. And it became apparent to us that even though, a lot of these hub heights for these towers were 80 meters, that the higher the turbine hub heights were getting, the more uncertain extrapolating shear would be from these Met towers. And we had recently entered into a JV in Ontario where we ended up doing about 1 gigawatt. And a lot of these projects were assuming higher hub heights, and actually when they were built, they ended up being 100 meters or more. And so we really wanted to look into remote sensing in lieu of taller Met towers. Those taller towers, they cost a lot more, they take a lot longer to permit, and they're not portable. So I want to describe kind of our initial foray into remote sensing. We were an early adopter of SODAR back circa 2006 or so, before my time with the company. We had one unit that we purchased. It was a non-Triton unit. I'm not going to state the actual OEM, but we deployed it at 2 different project sites over the next 2 to 3 years. The unit was costly to maintain and provided us with questionable data quality. It seemed like every time we were getting questionable data quality, we were advised something was wrong with it and to sink money into it, and we became very jaded with the unit. And so did our executives. They weren't pleased with the answers that we were giving them about why the unit wasn't working. They weren't pleased with remote sensing at all, and they were hesitant to continue purchasing or continue using that unit or purchasing additional units. So 2010 rolled around, and we were out attending conferences. My team was out attending conferences, getting involved in working groups with other companies, and it became apparent to us that our competitors were successfully deploying remote sensing, and we want to be on the cutting edge here at Pattern Development. That hasn't changed over the last 10 years, and we didn't want to fall behind in our practices. So we did some research, and our meteorological team convinced our executives to purchase 2 second wind Triton SODAR units. They're now owned by Vaisala, a decade later, but they were second wind back then. Both of these units were successfully deployed, and they showed promising results, and our execs began to warm up to the idea of using remote sensing for our development projects. So we get into 2012, and we've been using SODARs pretty successfully for the past couple of years. The wind speed values of the SODARs were promising at heights of 80 to 100 meters, but above that, data availability really became an issue. And it was pretty clear to us that maybe SODAR was good, but maybe not the best answer for heights over 100 meters or so. So our meteorological team investigated Lidar, and we investigated both the companies. There were 2 companies at that time, Lidars and Natural Power, that were offering units for wind resource assessment. And we actually secured a brief trial from Lidars because I said, I want to see how this works up against a Triton. So we had a development site in the eastern part of the country where we had a 60-meter Met tower, we had a Triton SODAR, and we were able to place a WindCube there at this site for a period of time. It was a short period of time, but it was accurate. It was long enough for us to see kind of what the WindCube could do. So this is a time series plot, and I hope everyone is able to see this. A couple of time series plots. This is this development site in the eastern U.S. You can see the Triton time series is on the left. The WindCube time series is on the right. The wind speeds here that are shown they start at 60 meters and they go up to 200 meters in increments of 20 meters. So for example, the yellow is 60, the red is 100, the blues are well above 100, and then you end up with pink at 180 and black at 200. So looking at this particular day, it's a 24-hour period on February 18th and 19th of 2012. You can see that during these low wind speed periods at the beginning part of the day, really the Triton's, struggling with anything over 100 meters. It does get better as the wind speeds pick up, and you can see the next 6 hours or so is through pretty good data availability through the column, and then it drops off again for whatever reason. For the last 6 hours of the day, you really don't see much above 60 meters. You look at the WindCube on the right here, same time period, and you have really great data recoveries all through the column, up to 200 meters for most of the day. I'm just going to show you again another day. This is a 24-hour period, March 6th and 7th, 2012. Same thing. Triton does really well up to 100 meters for the first third or so of the day. Gets better after that and records most of the way through the column and then kind of slacks off towards the end. Whereas the WindCube, you have every single level through the column all day. So seeing this, these time series plots and the other data that we were able to collect out there, really kind of sold us on, hey, lidar really appears to be a much superior product to the SODAR. So we decided to purchase 2 units from Leosphere and place them at sites where we were contemplating higher hub heights and really start kind of drilling in on our wind resource assessment. So we did that, and the first deployments in our fleet were in Q4 of 2012. Well, I want to talk a little bit about our LiDAR usage today. We now own about 15 WindCube LiDARs across our North American fleet. We also are deploying some remote sensing in Japan. We have at least one is planned in the works for a minority of projects. For example, we have at least one WindCube at every development project we have. We do have a couple of newer sites that we're contemplating getting them out there and in that process. We're using these LiDARs mostly for co-location or with Met Towers and for sheer validation by co-locating with those Met Towers. We have done some standalone use with the LiDARs and some areas where maybe Met Towers are hard to put, hard to install. We've put a LiDAR to see what we can see there. We've used we've done some limited power performance testing with them, non-IEC Edition 2 tests. We hope that as Pattern continues to do more power performance tests, that LiDARs will be incorporated. And then we're actually using a WindCube as in lieu of a permanent Met Tower at one of our Canadian projects. So issues to be aware of. With all of the really good things, there's always some cons, right? So we found that the WindCube units provide excellent data if they have access to a reliable power supply. It really took us a long time and a lot of trial and error to figure out what a good power supply could be. Obviously, grid power is preferable over everything else, but, as you can imagine, not many development sites have grid power. I think we've only been able to use grid power on one of our development sites out of all of them, which was nice, but not adequate. We needed to figure out another solution. We started out using propane generators to power the WindCubes, and that didn't go exceptionally well. Lots of issues with the propane, lots of issues with the generators. Just keeping them running was a challenge. We then incorporated to using fuel cells, and we did that for a few years with some better results. The fuel cells were powered using propane, but you still had to change out the propane every few months and be on top of that, and you really had to be on top of that. And it seemed like when one went down and we got it fixed, another one went down. And so there were also mechanical issues with the fuel cells, but they did work a little bit better than the propane generators. Over the last probably 3-4 years, we've been pretty extensively using these PV battery trailers. And what these are basically trailers that have lots of solar panels on them, or a few solar panels on them, and then they have batteries enclosed. You can see a couple examples of these trailers over here on the slide to the right. The first one is a site in Illinois. You can see the Met Tower in the background there. At least I hope you can on the picture. And the second one is at a site in New Mexico. And you can tell the one in Illinois also has a lot more PV on it, just because they have colder temperatures, lower irradiance up there. In this picture, funny enough, it's cloudy, so lower irradiance. So these trailers are available from a variety of different vendors. We've had pretty good success with them when stuff still does happen and stuff still does break, but usually it's a quick fix. These vendors will work with you to, talk to you about where your project site is and help you to size your trailer accordingly with the amount of PV and the amount of batteries that you need. And I also want to mention that a knowledgeable and reliable service partner is an absolute must for deploying and maintaining a wind resource campaign that includes LIDAR. I know that Vaisala provides some of these services. We've used some of these services before. They've done a good job. Another company that I'm working with, and I've worked with for the past couple of years, that does the bulk of this for us, is they're out of Denver, Colorado, a company called Harness Energy. They do a fantastic job for us, and we've enjoyed working with them, and we feel like we've been pretty successful working with them and getting them to quickly help us troubleshoot issues that we may find. So I want to talk about kind of what we're doing looking to the future. We want to continue to utilize LIDAR to further understand inflow conditions that drive turbine performance and operations. We want to continue to expand our knowledge and acceptance of scanning LIDAR technology. And these scanning LIDARs are, there's a myriad of facets that you can deploy them in. We've deployed a scanning LIDAR in Japan for an offshore project that we're currently evaluating the data for, and has helped us quite a bit with the wind resource assessment there. We've also deployed in operations a scanning LIDAR to look at wake modeling for an operating project, and that can really help us back in development. So one of the things we want to do at Pattern is create a feedback loop between our operating projects that tell us kind of how they're doing and help us to inform our future development projects. We also want to continue to collaborate with industry partners such as CFARs, which you'll hear about from our next speaker. We want to further advance the acceptance of remote sensing in complex terrain. So this is my summary slide. And really just, the problem we wanted to find something to help us figure out the wind resource kind of up there as 50 and 60 meter Met towers became outdated. The solution was that we deployed Lidars WindCube Doppler LIDAR coupled with a reliable power supply. That's a must. And we have been and we're still using WindCubes to assist in shear validation at all development sites. The data sets are being used more and more by the third-party wind resource assessors. And, we will continue using LIDAR as a big part of what we do in development. So I want to thank you all for your time today, and look forward to your questions. And I'm going to hand you back to Greg so that he can introduce our next speaker. Thank you very much.
Excellent. Thank you, Philip. I'd like to introduce now Renewable Energy Systems, or RES, as a global renewable energy company. They've been active in the industry for over 30 years, and for 10 of those years, Philippe has been focused on understanding how remote sensing can help his projects. Philippe is also the founder of the Consortium for the Advancement of Remote Sensing, otherwise known as CFARS, where he and other industry leaders are working to increase the acceptance of remote sensing worldwide. Before I hand this over, I'd like to remind everyone to please stay until the end, where Philippe, representing CFARS, is going to give us some late breaking news that I think will benefit all of us. Philippe, I'll pass it over to you.
All right, thank you so much, Greg. Hello all. So Phil talked a lot about the practicality of deploying a remote sensing unit. What I wanted to talk about is a return on experience from 350 deployments from RES, remote sensing device over 10 years. I want to discuss on how we can actually optimize the value of remote sensing device practically, especially answering the question on how you get back to your board or the investors and provide the confidence that what you're trying to achieve with the remote sensing device, you will actually be able to do. So we'll discuss that today. So just in terms of practical consideration, when you want to deploy a remote sensing device, it's very important that you understand what's the use case of your resource assessment here. So you can use remote sensing device in different capacity for shear validation or for spatial uncertainty reduction. And in order to be able to maximize the value, you need to understand very, very well what's going to be the characteristic of your site. So today, there's places where you could put your remote sensing device and make sure that you're going to optimize their value, and there's others that you can't do. One thing that you need to know is what's your site like. Is it benign? Is it moderate? Is it complex in terms of wind flow? Currently at RES, we use a metric. We say that across your cone, as you can see on your right, if you have less than 3% wind speed variation, then you'd be in a benign flow. And then you could probably use a remote sensing device for all the use case that you're looking at. Although there's no clear consensus yet on what is benign, and there's consortium today, like the Task 32, the IEA Task 32, or even CFAR, that are tackling that actively. And one of the key message I want to bring here is that if you want to get involved, you'll have a chance to do that, and you'll see later on how you push that forward. The second thing you need to know is you need to make sure that your use case, what you're trying to achieve, either shear validation or spatial uncertainty reduction, aligns with your site characteristic. For shear validation, today you could use your remote sensing device in simple to complex flow. For spatial uncertainty, you have two cases. You could be standalone with validation with a met mass. So you had a met mass on site, you do your validation. Then you could probably use it at another location in simple to moderate terrain. It's generally accepted. Now, if your site is simple, you could use your remote sensing device, and there's the third party actually define the different use case of remote sensing device, the NVGL, Vaisala, and the like, have actually qualified your remote sensing device as equivalent or not to a met mass in simple terrain, and you can read on that. But in this case, you could actually deploy your remote sensing device and not have a met mass on site. So that's the first thing you need to understand very well. The second thing is there's logistics involved in deploying the remote sensing device, and Philippe mentioned that quite a bit. But your remote sensing device is just as good as your power supply, so you have to take that into account. Now, just from a design standpoint, when you start thinking about your resource assessment campaign, you start to have this thing that's called planning, right? You need to think about how am I going to be successful with my remote sensing device and including it in my resource assessment campaign. Well, the way you need to look at it is essentially looking at your uncertainty level, and you need to reach a certain uncertainty level today to be market and be able to sell your project. So essentially it goes to the concept of your P99, which is your uncertainty, or P90 to P50 ratio. And there's standards over that. Like just as a case figure, we could think of a P99 to P50 ratio to be around 0.75 to reach your financing. So the things you'll have to think about is your measurement system uncertainty, your measurement duration to reduce your uncertainty, your vertical extrapolation. So how high do you measure above your measurement? For remote sensing device, you measure at hub height, but there's also the horizontal extrapolation uncertainty. So how many measurement points you have. Then you combine that with your inherent uncertainty for the project, so your production uncertainty. You can think of things like what are going to be your turbine degradation and all of that. So those are all associated with other uncertainties. So if you combine that with the things that you control when you design your wind resource assessment campaign, then you can come up with some PXX P50 ratio. Now, the one of the things that you need to think about is all that needs to fit with your project management schedule. So you have a budget, you have health and safety requirement, and you have a timeline. And you want to make sure that everything fits within that. Now, here's what could happen. If you've designed well, you'd be in the last part of your box. So basically, you wouldn't meet your threshold that you've set yourself to finance your project. In that case, you need to keep refining. So measure longer or more measurement. You'd like to avoid that as much as possible, obviously. But if you exceed your threshold, you're good. You can bring the project to market. Now, at RES, some of the consideration that we have when we design our resource assessment campaign, obviously costs and timeline, but at the forefront, because we're also a construction company, there's a health and safety consideration. And one of the reasons why we're moving towards remote sensing device more and more is those striking statistics, in my opinion, is we record our accident and near miss. And if you look at the very far right of this table, the masts have been considered as a much riskier business than remote sensing device. Obviously, remote sensing devices are not perfect. If you look at property damage and vandalism, which is the last row of this table, there's quite a bit more vandalism on remote sensing device simply because they're more accessible. There's ways to avoid that by adding more safety to it. So that's one of the reasons why RES in the next years are going to put a big emphasis to a remote sensing device. Now I'd like to bring this slide as well, which basically explain how you can improve your resource assessment campaign from the get-go. So what you're seeing here is a typical layout with 90 turbines, and the orange dot are met masts, 60 meter in height. The hub height in this case would be 105. And so the idea here is on a classic measurement campaign, and this is a theoretical exercise. Imagine that the site is perfectly flat. There's no complexity. If there's complexity, on the site, there's probably a need for more measurement, but imagine it's perfectly flat. Then if you had 4 60-meter met masts, on those covering those 90 turbine layout, then you'd reach your P99 P50 ratio of 0.75, which should be market. The cost of that would be about $280,000, and you'd have to measure for 2 years to get to that point. Now the question is, can you actually improve on it? So basically, improving your project management standpoint, from a project management standpoint. So your timeline, your budget, and your health and safety. Can you improve on that using remote sensing device? And this is what we're going to look at in the next slide. So if you had to add remote sensing device and you're trying to achieve the same P75 P50 ratio, here's one option. What you could do is you could install 260 meter mast, and you'd had for 1 year a remote sensing device to actually get the measurement directly at hub height. The total cost of that would be $190,000, and you could do that for 1 year. And what would happen is that you would reach your 0.75 ratio. So you'd actually improve on your timeline, you'd improve on your cost, and you'd have 50% fewer towers. So in our opinion, from a RES perspective, it'd be safer. The other option that you could use, so that's the second case on this slide, is to actually have one mast, and you'd co-locate it with a remote sensing device to have the measurement at hub height, and you'd validate your remote sensing device against your mast at the same time. So you measure for 1 year, and then you'd move your remote sensing device for another year at a second location to improve your spatial uncertainty. And you measure for another year, and you'd get to the same level of uncertainty. So that would take you 2 years. So you don't save there, but you have the same type of time duration for your measurement, but you'd save on cost, and you'd have 75% fewer towers, so safer again. Finally, you could use another strategy, which is, let's say, more forward-facing, where you deploy standalone 3 RSDs. Now, I remind you that you're on a very simple site. With 3 standalone remote sensing device alone, you'd measure at hub height at the 3 points, and after 1 year, spending about $148 you'd get to the same type of uncertainty. Now, that being said, RES has used these 3 methodologies successfully to to get bankable and finance projects around the world. One place where we still have a little bit of discussion is around the US with the production tax credit, but we're having discussion with the investors, obviously, on using the third approach, which is remote sensing device only. So one of the goals that we set ourselves internally, just from a health and safety perspective, and when the site can actually accommodate it, is to finance one project and get bankable report from major consultant in each of our markets. So we're present around the world. So we're trying to push that forward for the reason that I've just mentioned. Now, there's another thing that we need to discuss, I think, is RES is not only pushing for, in the right context for remote sensing device from a budget and health and safety and time consideration, but we also think that remote sensing device provide information that traditional measurement don't. So the anemometry with a met mass won't be able to provide. So one example of that is the great work that the Power Curve Working Group has done, also leveraged by Andy Clifton back in the days in NREL. So essentially what it is that currently when we're predicting power, what we're doing is we're using one parameter, and that parameter is the wind speed at the hub height. Now, you can think that climate is much more complex than that. Wind speed varies with height and all that. And if you think about it, what the LiDAR and SODAR can do that traditional anemometry can't do easily, especially when you get to the very tall tower, large rotor, is to provide information at different level. So one of the work that was done back in the days by the Power Curve Working Group is that they looked at the error in the power prediction that you can see on the left box using traditional ways of looking at power output, and they came up with those box plot with an average error and all the deviation around it, and they added some parameters to it, like the standard deviation, but they didn't see much improvement. Now, when they started to import what the LiDAR can do and having measurement at different level, and using much more complex prediction analysis on what's going to happen in terms of power prediction. So a different statistical model like neural network, random forest, et cetera, and artificial intelligence, these saw quite an improvement. That's just a reason why we think as an industry we can benefit from those new techniques if we embrace it right. And the other ways you could do it in pre-construction, if you think about it, is you could, and this is just one way to think about it, but it's just to get the crowd thinking about what's the value of remote sensing compared to traditional ways of measuring. Is, for example, if you had to train a LiDAR on one side with a prototype turbine, what you could come up with is a theoretical like power curve that would have multiple types of inputs, like different level. You could think about temperature. You could think about the actual humidity in the site and all that. You can start thinking about everything you could input there, and you come up with like a multi-dimensional power curve, which would be more accurate in theory than the ones provided in pre-construction from a single point. The other thing is that when you do that, you trump some major uncertainty when you try to compare your LiDAR to a met mass. So they're fundamentally different. You don't need now to train it against a met mass or compare it to the met mass. If you bring it to another site and you start combining it with the actual climate at that site, what would happen is that you theoretically would reduce a lot of the uncertainty, and at the end, you'd have less investor risk, and that would be something that would be desirable for our industry in general. That's a work in progress that RES is tackling, and we're hoping to start presenting some results through the different working group very shortly. The other reason why we're pushing for LiDAR is you can imagine if you don't have measurement above if you don't have the measurement at the hub height above where you're actually measuring, so you can think of a Met tower, which would be like anywhere between 100 and 80 or 110 meter, or even 60, then what would happen is that you don't have really good ability to know what's the climate above your tower. The reality is that right now we have ways to compensate for that using remote sensing device and understanding what's the shear profile above your measurement point up to the hub height with those towers that you could perceive as being as high as 120 meter in the next generation, and in certain market it goes actually much higher. And so one thing that we've done is we had the luxury to have 17 high quality mass remote sensing pairs across the United States, and we looked at these co-location that were there for more than 1 year. And what we did, we just did a simple prediction of what would be the wind speed predicted with the met mast, the small met mast, and what would be the remote sensing device. And as a response to many of the concerns that the investors have today, which is basically saying that if we introduce remote sensing device, the only one thing that we're very concerned about is that you don't introduce, for example, systematic bias in the way that we are measuring. Well, that study showed that if we're actually not using remote sensing device, we're at risk to actually introduce bias, because for most of these masts, what we've seen is what we call shear relaxation. So if you use the shear that was measured with the mast at the lower height and you predict up, you'd have an over prediction. And if you use the remote sensing device, then you realign with what we think the wind speed is at the hub height. And what we found is about a 0.9% over prediction when we use the mast alone in wind speed, and about 1.8 in the energy. So that's one reason why we're pushing for remote sensing devices, to provide investor with more confidence, and we think that's one way we need to do that. So in conclusions, we think at RES that we now have a large body of knowledge around remote sensing device for for resource assessment, and we have various options to bonify measurement strategies. The remote sensing device delivers cheaper, faster, and safer resource assessment campaign. It doesn't compromise quality as long as you understand the use case. And that is important. We need to come together and define clear consensus and guideline around the use and the acceptability of remote sensing device. And I invite you to get involved, because the learning there will be great. And I think there's a lot out there, but it's just consolidating that and making sure that we all agree together and we push forward in the same direction. And remote sensing provide ways to further de-risk production estimate through innovative concepts like AI and statistical methods. I want to thank my colleague Rory Curtis that worked really hard on these concepts. He's pushed the remote sensing device development and understanding at RES for the past 10 years. That's something very important to me as we're moving forward. I think this is the type of collaboration that within each organization we should cherish, and make sure that we bring all these people together to push forward the industry. Now, if that's okay, I'm going to talk a little bit to CFARS. I have still like 5 minutes to go. Discuss CFAR very briefly, and the reason why it's being formed. So CFARS is the Consortium for Advancement of Remote Sensing. RES was keen to actually form a consortium in pushing the limit of our understanding of remote sensing and bringing all the players together to share the information that we have and make sure that we provide more confidence to our boards and our investors. So CFARS is moving forward. It's been running for 2 years, and there's now over 20 companies involved. And you'll see that there's more to come. CFAR's mission is to increase the acceptance of remote sensing, reduce project development costs, and reduce uncertainty around our estimates using remote sensing device. We want to contribute to the competitiveness of the wind industry as a whole by 2021. So you can understand in the States, that's when the PTC ramps down and it's going to be less subsidies to wind across the globe. And so we want to be able to provide some more competitive advantage there. Our values were open, we're collaborative, we're result-driven, and we want to provide leadership. So you're going to see there's subgroups and there's champion. We're actually delivering results, concrete results, and quickly. Here's the roadmap of CFARS. In the short term, we want to provide guidance, as you probably are aware, some of you, and if not, you will be able to go and see the results of that on the website. But we've actually probed the industry with surveys to know where exactly we should work for greater acceptance of remote sensing. And we've done that last year. We identified like 3 areas that we should work. One is complex terrain. The other one is site suitability, namely the turbulence intensity, and the other one is power curve. So all these findings actually get transferred to the science group to actually work on these things with the other consortiums. So as you can understand, there's the IEA Task 32 and there's some joint industry partnerships that are working. So all the good results that we're generating are shared. But the reality is that CFAR is a body of people that come from the private sector that can share information and accelerate the acceptance of remote sensing device. And though we are right now at this crossroad between the science and the guidance, and we're going to the acceptance criteria whereby we want to formalize our results. And for that, we'll need all of you to buy in CFARS, buy in the results that are going to be shared through us and through the other consortium and make it through consistent. So we have two groups, the guidance group and the science group. The guidance group is led by Matthew Mayer. There's the baselining has started and the acceptance is started, as I've mentioned. You'll be able to all get to Matthew. You'll see the contact information very soon. And there's the other one, which is the science group. And there's a breaking news is that the science group have 3 major sub-work stream that we're working on, the flow correction, the site suitability, and the power curve. Flow correction has actually moved very fast under the guidance of Alexandra Sampey. And you can find the early findings that you could be involved there as well. And site suitability is also moving. Where we needed a little bit more, and we are actually moving forward, is the power curve. We've identified with the power curve working group that you're very familiar that we now have a common mission. And we both agree that the future for power curve measurement is going to be done through remote sensing device. All the good work that they've done in the past with traditional anemometry is wrapping up. There's still some small thing that needs to be done. But what we're going to do is we're going to share our momentum and energy, and we're now tackling the future together as a group. And so those people that are in the power curve working group are going to keep operating through the ShareX, but we're going to actually join forces, which is in a very good news, and I'm very enthusiastic about the future. So please get involved. So there's going to be next meeting. You're going to see soon on complex flow, RSD acceptance, power curve, and you're going to have an update on the general activities. In the next year, we're going to have 2 in-person meetings, one in the US and one in Europe. And so you'll know soon. So if you want to know more and you want to get involved, please reach out to either me, Alexandra Sampey, or Andrew Asting Black. We need people because we're going to start having some public funding, or we're going to seek for public funding, and we will actually get more information with the IEA Task 32 to actually push forward our group. We want to formalize our early TI load and complex flow findings. And again, please get involved, get your goodwill in. The future is now, and if you want to be part of it, you might want to actually reach out directly to our CFARs or Power Working Group organization. So thanks for your time, and now I'll turn it back to you, Greg, if you have any questions. And please, you can also reach out directly to me if you want to know more about those two consortium.
Excellent. Thank you, Philippe. Looks like we have about 15 minutes or so to address some questions. And I'm just looking through the question chat here. Have one, Philip from Pattern.
Yes.
There's a question about how how does climate affect your LiDAR and data quality? Maybe that's a good one for you.
Okay. Well, with LiDARs, it's really about what sort of particulates that you have in the air. So the laser beams are going up, and they're being reflected back to the unit off of the particulates. So I would say that sites with it may not be so much as climate like warm, cold. I would say sites that are have clearer air or cleaner air. For example, we've used the LiDARs pretty extensively in Canada. And some of the sites that are out in the middle of nowhere and have cleaner air, the data recoveries aren't as good. They're still very good, but they're not as good as you would see at a site that has more particulates in the air. Those are the sites that really the data quality is exceptional.
Okay. Excellent. Thank you for that. There's a question here. Philippe, maybe this is a good one for you. So how long does it typically take to fill the bins to complete a LiDAR shear validation?
So there's different philosophy around that. It really depends on what I would qualify as interannual variation. So if you have lots of interannual variation, you can think of a climate where things change quite often. I can think about the northeast of the United States, for example, where you have lots of variation between winter and summer and all that. Then I would encourage to have a longer shear validation. I mean, in order to reduce your uncertainty, if you want to take the aggressive case, you could use 3 months, and you'd probably be able to reduce your uncertainty around above measurement extrapolation, right? But if you want to be safe, particularly when there's some variation, I would encourage you to go to 6 months. And then if you're interested, and it becomes more into the R&D side of things to understand better your climate, which is not a bad thing actually. If you have it on a site, you could actually co-locate your remote sensing device with your mask, for example, to understand the shear better. And you could probably use a year, but as a safe bet, I'd say 6 months is good. But if you don't have the luxury to deploy that remote sensing device for 6 months, you could use three months with caution.
Okay, thank you. So there's a few questions here, and maybe both of you could comment on this around the length of recording using a LiDAR. Would you recommend to use it in shorter deployments and maybe move it around, or are you still mainly using it as, say, in a fixed location for a 12-month period? So maybe Philip, you could give us your answer to that, and we can pass it over to Philippe, because I know people have different opinions on this type of question.
You're right. There are different opinions, and I don't know that there's necessarily one right answer. Pattern development, we're using our WindCubes in a standalone location, or with a Met Tower. We put them in those locations for about a year, and then we move them. We want to make sure we capture any shear changes with seasonality, and so that's why one of the reasons we do that. We don't typically do much of anything shorter.
Right, and Phil, we're similar. I think the question was around like where you think there's more value, and again, it really depends on the context. And this is going back to this slide where I'm saying plan, and understand what you're trying to do. But I think maybe one insight for the crowd here, and I'm open for discussion, is as we're getting to a higher and higher hub height, we've seen that one of the highest uncertainty on your site is really the extrapolation. So if you don't have the luxury on a site to have a measurement at hub height, one of the best bang for your buck as you use a remote sensing device is to get that information. It quickly reduce your uncertainty, and I think we've seen that as one of the main driver, particularly when you're getting to a 110 and above hub height, which is frankly the future. Now, the reality is when you're planning your measurement campaign, there's various consideration, and you've been all there where you put one measurement and then you need to quickly increase your spatial coverage. And one of the things that is really useful by using a remote sensing device is if you have the right site, you can trump a lot of the key consideration, which is like permitting a met mast, getting like complex agreement with some landowner and all that. So I think in that respect, this is where you can actually get a lot of value of remote sensing, is how quick and nimble they are in their deployment. That makes sense.
Yeah, it sure does. Here's another question. I think I'll take this one. A few years ago, we purchased a WindCube from NRG. Where do I get it serviced now? So this is actually a good question. NRG was the reseller for Leosphere WindCube products before Leosphere was acquired by Vaisala. And they did an excellent job over the years servicing those units. But today, you can get direct support from the manufacturer, from Leosphere, from Vaisala. You can reach out to me if you have any questions on that, but we are completely geared up to service and support both the legacy WindCubes or the other WindCubes that are out there, as well as obviously the new ones that we introduced at the beginning of this year. Moving on here, we have Philip, here's an interesting question for you. Do you have an example or a thought around when not to use a remote sensor?
When not to use a remote sensor? Well, you know, I think that there could be a lot of ifs and ands or buts on that question, that way to answer it. I think maybe if, you know, you're contemplating maybe lower hub heights, not that really a lot of people would, but maybe you wouldn't need one in that respect, like the way we used to finance projects. I would say, you know, it could be tough. There's a lot of challenges about the type of terrain that you're in. So, for example, if you're in somewhere in Canada, northern Canada, or maybe you're in northern Japan that gets a lot of snowfall, that makes it basically inaccessible, the site inaccessible for the majority, you know, maybe 4 to 6 months out of the year because of that massive snowfall. I wouldn't say maybe you wouldn't want to use it, or at least try to use it, but it's going to be a significant challenge if something were to happen to the unit during that period that the site's inaccessible. So you may want to rethink your strategy there. Granted, you know, it could be tough depending on the type of turbine that you're wanting to use, but accessibility could be site accessibility could be a big driver on using one or not.
Sure.
Yeah, I would abound. I would support that. I think that's right. I would also caution still on very complex terrain, although for sheer validation it could be helpful, but I would caution about that. But for the rest, I think remote sensing device, I mean, I would advise it almost unilaterally, in my opinion.
Yeah, same here.
Excellent. We have, for Philippe, someone was asking a few questions around the scanning LiDAR. They understand that scanning LiDAR has been used for offshore and was wondering if there were any other applications in which it would be useful for onshore. Let's be for both of you, actually, because go ahead.
Yeah, I can answer some of that, Greg. So I think first, I think scanning LiDAR is the next generation in terms of applicability in the commercial world that we're working on. So basically, you need to finance your project onshore. There's still some challenge here. I can just mention that CFARS today is handling the current technologies available that could lead to finance a project. We're hoping, and that's vertical profiling LiDAR onshore, but we plan, if we can close that, to tackle the next generation. It'd be really nice to have that from. So there's still a challenge. I can see, though, some applicability, especially in simple site where you could actually understand way better what's happening in very unusual flow. The scanning LiDAR will help you to understand that when there's like non-stable flow and all of that. Technically, we could actually map all these things and start to draw a conclusion whereby we could have some difference between our pre-construction estimate and post-construction. So yes, there's definitely a lot of goods to it, and I know offshore is using it, and there was cost incentive to get there. Challenge onshore, it would be to bend the cost of that technology further and really understand how you bring it to a stage where the investment crowd would be comfortable with it. But we need to get there. That's my opinion.
Okay, thank you. And Philip, I know you had mentioned you were using scanning LiDAR.
Yes, we've successfully deployed a unit in Japan for an offshore facility.
Right, and there's a research project on onshore deployment. There's two, actually. One with the Techno Center. It's a research, well, it's actually now Nergica. It's a research facility based in Quebec, Canada. And there's the Recast project, which is done with the RESO. I think the Res is part of that. I think we're slated to have results in the next year, but I encourage you to go and look at those two if you want to have more information. They're also a really good body of knowledge.
Okay. Well, we just have a few minutes here, and I want to thank you, Philip and Philippe, for your time and, just sharing this information with the rest of the industry, and really encourage people to check out CFARS and join in this information sharing and join and help advancing the use of remote sensing. I'd like to thank all the people listening in on this call, and a very special thank you to AWIA for hosting this webinar. So with that, we will conclude, and everybody have a great day. Thank you.
Thank you.
Thank you very much.